right. Good evening, everybody. I'm kind of waiting for people to arrive here. All right. Well, I guess I'll get started. It's 7 o'clock. You folks are on time, so we'll start on time and let other people hopefully come and join us. So welcome to Seattle Friends of Fission's talk on climate change, the future of energy in Washington. And Seattle Friends of Fission, for those of you who don't know, has been putting on talks, public talks, for about 5 years. And of course, we're on Zoom with COVID. Before, we were in lots of different places around town live, which was lots of fun.
Yeah.
And we talk tonight, it's going to cover all the interacting uses of energy in Washington state and what needs to be done to assure an ample supply of energy in the future. So our speaker is Dr. Jim Conca. He's an earth and environmental scientist specializing in geologic disposal of nuclear waste, energy-related research. He's done work on issues in space, and he's been at this for at least 34 years, probably more by now. He's been a consultant for the DOE, Department of Energy, EPA, state environmental agencies, and industry companies, including nuclear, hydro, wind farms, large solar arrays, coal, and gas. He currently writes an energy and environment weekly column for Forbes.com, which is great. Folks should think about checking that out. That's always interesting things, and you can look at past ones for lots of back information. So Jim, it's yours.
Well, sorry, let me butt in really quick and remind everyone that we are recording and broadcasting to a variety of different places, including the Seattle Friends of Fission Facebook group. Take it away.
Good, thank you. Yeah, this is the kind of stuff I talk about or write about on Forbes. So if you want to get a little bit more info on any particular subject, just Google Conca Forbes and then whatever subject, whether it's nuclear or wind farms or whatever. And I should come up in the first page there several times. Yeah, so let's just kind of get started. I'm going to share my screen here. And we'll go with this. My spouse and colleague, Dr. Judith Wright, and I started working in this area of kind of a holistic view of energy issues about 15 years ago. And it's been very interesting because most people are stovepiped. I mean, everyone has their main interests, their main expertise, and they kind of don't see the bigger picture. And energy is one of those issues where you have to see the bigger picture. It is too complicated. It underlies every aspect of society, and it underlies every subject area. I mean, you can talk about the physics, you talk about the technical issues, but the history, the economics, the politics, I mean, it's everything. And it's hard to separate energy from any of those things, especially history, because things evolve historically, societally, in a way that people don't realize determines the future. I mean, you just can't pick up and change direction easily when you're talking about generating 25 trillion kilowatt hours a year over the planet. So it is a complicated subject. So we're going to talk about tonight kind of what's the state of the energy issues in Washington State and the Pacific Northwest. Now, one of the issues is Pacific Northwest versus Washington State. This is what the energy industry considers the Pacific Northwest. So down onto the border of Arizona. So that's not what I consider the Pacific Northwest. But when you're talking to the Bonneville Power Administration or to other independent system operators and things like that, this is what they consider the Pacific Northwest, because we're all tied together here in this area. Now, we're talking about Washington State, of course. We're just talking about Washington State. So I'll kind of flip back and forth there. And we are somewhat, we're all linked, but we're significantly different state to state out here. The Pacific Northwest I just want to throw this out. We are facing a significant shortfall in power generation in the next 5 to 10 years. Significant, to the point we're going to have rolling blackouts. There's just no way around it. Just like California had this year and Texas had this year because of bizarre weather. So what we need to figure out is how we're going to deal with this. And the system operators and the Pacific Northwest power groups, they're all very, very worried about this and trying to deal with it. At the same time, we're enacting legislation that essentially discourages, if not outright outlaws, new generation that generates carbon. So that, this is not a trivial issue. And this is where I say the holistic view matters, because you just can't willy-nilly outlaw things without understanding how you're going to replace them. And if you don't replace them correctly, then you're going to have rolling blackouts, which is dangerous in many ways. So this last heat wave we had at the end of June, we actually were quite close to rolling blackouts, unknown to most people. Heat waves and cold snaps are where everything really gets tested. And where you have to have the extra capacity to deal with the demand brought on by, a lot more air conditioning going on or a lot more heating going on because of the extreme cold or heat. And so even though 95% of the year you might be just fine, it's the 5% that matters. You have to have resources adequate to handle the weird 5% of the time, or it doesn't matter what the other 95% did. Okay, do you understand that? It's sort of that last kilowatt that you need determines everything. And if you don't have enough in that 5%, then you're going to have rolling blackouts during extreme cold or extreme heat. And that's when people die. And that's when crops go. And that's when a whole bunch of things happen that are bad in just these extreme of heat or cold. So the reason we almost had rolling blackouts is the same reason California and Texas did have rolling blackouts, because they did not have adequate resources. So the near-term problem, shortfall, is about 3 to 7 gigawatts. Now, a gigawatt is, I should kind of step back a little bit. There's watt and then there's watt hour, okay? Watt is a capacity. That means you may be able to generate a watt or a gigawatt, which is 1 billion watts. You may be able to generate that at any one moment, but the gigawatt hours that you generate throughout the year is what you actually generated. So there's a potential. So think of watt without the time associated with it as just a potential. That's what you could if things were going great, okay? But the watt hours is what you're actually generating, and that's what you need to generate in order to have things operate the way you need them. So if we talk about 3 to 7 gigawatts, that's 1 billion watts. You could say that's a million kilowatts or 1,000 megawatts. Okay, so if we talk about 3 to 7,000 megawatts of capacity shortfall, then that would be 3 to 7,000 megawatt wind turbines, all right, as a capacity. That would be 1,000 megawatt nuclear plant. That would be 2 500 megawatt gas plants. So again, this is what we're short. So we're going to be short in the next 5 years of the equivalent of the nuclear power plant out here, or all of the wind in Washington State. We'd be short that amount. We're going to be short about 2 gas plants or a coal plant like Centralia that is closing. And that's one of the reasons that we're going to be short, is because Centralia is closing that 1,300 megawatt coal plant in Centralia. So that's the short term. So we need to deal with that right away. That's not all that much. Midterm, the next 5 years, 2025 to 2030, we need 10 gigawatts more. That doesn't include the 3 to 7 here. We need, beyond this, we need another 10 megawatts, because we're closing things, and we'll talk about that. Even in in the optimistic scenario, okay, we're going to still be short. So if we put in new generation that we're talking about, new wind farms or new hydro or new nuclear or new whatever, we're still going to be short, even if everything goes in the way we want it to in the next 10 years. So optimistically, we're still going to be 3 gigawatts short. Long term, 2030 to 2050, we're going to have some real problems because we are trying to deeply decarbonize the grid. So we're trying to get rid, by 2050, 2035 actually, 2050, we're trying to get rid of all carbon producing electricity generation. And that is really going to be tough. And we'll talk about why. So one thing you must remember is that electricity simultaneously is produced, it's delivered, and it's consumed all at once. Okay? It has to be balanced. If it is not balanced, you will either start blowing transformers or start having rolling blackouts. So if you have too much produced and it's not consumed, you have to shut down capacity. You must stop producing more energy than it is used, it's consumed, or you'll start blowing things up. If you don't produce enough than is consumed, then you'll start having blackouts. You just don't have enough to run everything. So it's very bizarre that these system operators like BPA and others, they're pretty much sitting in front of a computer screen, turning things on and off and balancing and making sure everything's fine. When a whole bunch of wind comes on, you have to shut down something so you don't overproduce. Then when the wind stops blowing, you have to bring something up online to take care of that loss of that capacity. So it is an amazing system that we have. And it's amazing that it works without having rolling blackouts all the time. I mean, it truly is quite an amazing system we have. Now, one of the reasons it's been amazing is because we've had a lot of capacity that can generate when we want it to. We can turn it on and off, like gas or coal. If we're replacing that, now we're going to have to use things that we can't turn on and off when we want it. We have to wait until the wind starts blowing or the sun is shining, or we have to store it for the times that they're not. So we're entering an era, self-imposed, where this is going to be much more difficult. And it's beginning to be difficult in California, which is leading the way in getting rid of generation and bringing on new intermittent generation like wind and solar. They are finding these problems now, and hopefully we will learn from them. Let's see. Now, something I want to talk about, capacity factor. So these are the capacity factors that DOE measured. These are actual operating capacity factors averaged across the entire country. It depends on where you are, and I'll talk about that. But capacity factor is the annual average. Come on, get out of here. Stop. Okay, the annual average percent of the maximum output possible. Okay, so if you have a 1 megawatt wind turbine, and it has a capacity factor of 34%, which is average in the United States, then that means 34% of the time it will produce 1 megawatt. That's it. It won't be producing a megawatt 100% of the time, about 34% on average in the United States. And so the same thing with hydropower. This is lower than one might expect because hydro does so many other things. It's involved in navigation and flood control and irrigation and fish passaging and things like that. So it's very in flood control. So we can't use all the water 100% of the time to generate electricity because we use that water for other things. Okay. Coal's about 50% almost, natural gas a little bit more. Nuclear is always running. So nuclear has the highest capacity factor, meaning it's producing the maximum it could produce over 90% of the time. And the nuclear power plant we have here in Richland, it's about 99%, which is rather amazing. So you can depend on it. You only have to stop a nuclear plant once every 2 years to refuel, and it shuts down for a month to refuel and do all the other maintenance that you've wanted to do for the last 2 years. So it's pretty much running all the time. Solar is the lowest, of course, because you can't control the sun very well. And the efficiency is just kind of physically determined by the technology. So again, these are the capacity factors. Now, if you look at a wind farm, say you have a 200 megawatt wind farm, okay? That's the installed capacity, 200 megawatts. You multiply that by the capacity factor, so for wind is 34.8%, times the number of hours per year to get the amount of power produced by that wind farm over the year. All right? So you do this with any generation source. You must do that to figure out how much it actually makes, because you can't compare apples to apples by just looking at the capacity without the capacity factor. So if you look at the nuclear power plant out here, 1,000 megawatts, it runs over 90% of the time. So every year, this power plant produces, actually it's closer to 9 million megawatt hours per year. All right, that's what it does year after year, about 9 million. Wind, 1,000 megawatts, same installed capacity. So you're talking about 1,000 1 megawatt turbines or 500 2 megawatt turbines. So, but you have the same capacity as this nuclear plant. In the Pacific Northwest, I should actually show that. In the Pacific Northwest in eastern Washington, the capacity factor for wind is only 27%, okay? And that's the historic average. That's all it ever gets. If you're in Tornado Alley, say in the middle of the country, Kansas, Nebraska, you're going to get 45%. So it actually matters where you put wind turbines if you want to get a maximum amount of energy. You want to put them where the capacity factor is larger. But in eastern Washington, it's about 27%. So if we have wind turbines in eastern Washington, and it's mostly the same in western as well, then you're only going to produce a little over 2 million megawatt hours a year for the same installed capacity. You see that? This is very, very important. That means when you're talking about you're having a shortfall of, say, 1,000 megawatts, well, it depends on what you install to meet that shortfall. Because if you install 1,000 wind turbines, you're not going to get the same amount of power. So you're going to have to install about 3 or 4 times the amount of wind turbines as nuclear. Or you're going to have to install twice as much wind capacity as coal, or 3 times as much as natural gas. So in solar is even worse. So you need to understand when you're talking about gigawatts or megawatts, that's just the nameplate installed capacity. It doesn't tell you what it's going to produce. You must know the capacity factor in order to plan how many of these you need to make. So when people talk about cost and they compare 1,000 megawatt wind farm with 1,000 megawatt nuclear, they compare these two and they think they're comparing the same cost, and they're not, because you have to install 3 times that. All right? Or you're going to be sorely disappointed when you need that energy. Okay, so you got that. Now, if we look at the Pacific Northwest, not Washington State, now we're talking about that big chunk that was the Pacific Northwest. We have the nameplate capacity. So this is the gigawatts, okay? This is the nameplate capacity. And then we have the effective gigawatts, which in this is from the Northwest Power Group. They call it effective gigawatts, but we're talking about the capacity factor corrected for. So the nameplate capacity, fossil fuels are about 1/3 of the nameplate capacity. And wind is pretty high. I mean, that's pretty up there, and hydro is high. But when you look at the effective capacity, fossil fuels are 50%, okay, because they have higher capacity factors than all these others. And these don't, well, nuclear, of course, has, so here's nuclear, it actually expands in its effectiveness, as does coal and natural gas. Hydro goes down because hydro capacity factor is only about 40%. And then, of course, wind and solar are really small because their capacity factors are so small. And as a result, we have to import more. So again, this idea of what the nameplate, the installed capacity versus what's actually produced, you got to keep that in mind. I'm going to stress this a bunch because you must keep that in mind. Otherwise, you're going to have rolling blackouts, and you'll wonder why. All right. So because of that, because capacity factors are not 100%, there's something called load following or buffering. So if you have a wind farm and the wind stops blowing, then the electricity produced or the power produced by that wind farm stops. I mean, it just goes down to almost zero, if not zero. And so, again, as I mentioned, the system operators are watching this, and they flip on a natural gas fired power plant to take over, or they put more water through the turbines in the hydroelectric plant to be able to buffer that or load follow it. So if more renewables are coming onto the grid, you're going to have to do more load following, do more buffering, because they're going to be going up and down all day long, all week long, all year long, okay, because they're intermittent. So this is what everyone's worried about. And again, you have to completely balance the grid, okay? So this is what happened in Texas and California this year. That's why they had rolling blackouts, because they did not have the backup generation, the load following ability to take care of the grid when the solar and the wind went down during heat waves or cold snaps, as in Texas. So usually natural gas is used to buffer wind and solar, because natural gas is one of the few things you can flip on and off like a light switch. Okay. Now some gas plants you can't, but the gas plants we use, we call them peaker plants, because when suddenly you have a peak load, you need to flip something on, and it's natural gas. That's what we use in America. Okay. Now coal, China uses coal to do that. Germany uses coal to do that, and Texas uses coal to do that, and parts of the Midwest. And the Pacific Northwest, Eastern Canada, and parts of China, we use hydro. So in Washington State, the Pacific Northwest, we use hydroelectric to buffer wind and solar. Okay, because we don't have much solar, so mainly wind. So when things get rough and suddenly we lose a whole bunch of wind capacity, we use hydro. Okay, so we put more, instead of spilling water over the dams, we put it through the turbines. Pumped hydro storage, actually it's 95% of global storage is pumped hydro storage. And I don't know if you know what pumped hydro storage is, but it's when wind turbines or solar are producing energy. You have a little hydroelectric plant up high at an elevation, and you use that excess energy from wind and solar to pump water into the reservoir behind that hydroelectric dam. And then when it gets dark, or when the wind stops blowing, then you let that water out through your hydroelectric dam and you produce energy. That's how you store wind and solar, using pumped hydro. Now you lose a bit of that in efficiency, but that's okay. It's actually quite a good system to use. It's better than batteries. The amount of batteries we have to store power in the world is still negligible. I mean, it's not even, you can't even measure it. It's so low. So pretty much most of our storage is pumped hydro storage. Now, new small modular reactors are specifically designed for load following. So the ones at NuScale or TerraPower, Bill Gates's nuclear power plant, nuclear company, they're designed specifically to load follow renewables, because they're designed for the future. And the future has a lot of renewables in it. Sufficient batteries are not available, and maybe by the end of the century, but we just don't have enough lithium, cobalt, or graphite. This is one of the big issues. We don't even have enough to expand the electric vehicle industry the way we have to do it in order to get rid of petroleum. So, again, this is not talked about much, but materials are a major part of this. Exotic, critical minerals and materials are needed to get to this new future, low carbon future, and we don't have those yet. Now, in the Pacific Northwest, during droughts and heat waves, we're in danger because we don't have enough water during a drought. And just again, the heat wave we had this last June put a huge stress on the system near the point of failure. And BPA said it was very lucky they didn't have to implement rolling blackouts like they did in Texas during the cold snap in February. So they were just lucky. We were very lucky. That's the problem when hydro is a huge part of your installed capacity, is that now you're suddenly susceptible to low water amounts during droughts. So this is not a trivial thing. And with global warming, that's going to be a problem as well. So when we talk about load balancing or load following or buffering, this is what we're talking about. So this is an average week. It's called the load graph from Bonneville Power Association. This is for the Pacific Northwest. Again, not Washington State, but the Pacific Northwest. Let's just kind of go over this. The light blue is hydroelectric. So this is gigawatts. So this is second by second gigawatt amount of energy being produced. So this is a billion watts. And so we see, okay, let me back up. The load is in gray. So we see the load. The load is the draw. This is what's being consumed. This is what the grid is providing and what we are pulling off the grid to cool our homes or run our businesses or charge our iPhones or whatever. This is the load. This is what we need, okay? So what Bonneville Power Administration and all the other independent system operators and regional power operators, they're looking at the load and they're trying to balance it. They're trying to provide the amount of electricity to balance that load. So here's hydro. Hydro is light blue. And you notice, I mean, it produces more than the load, but then there's efficiencies and blah, blah, blah. I don't want to get into how it's distributed. But hydro is essentially, 70% of our load is provided by hydro. In the Pacific Northwest, we have so many hydroelectric dams. So, and as you can see, the hydro just follows load directly. I mean, when load goes up, hydro goes up, load goes down, hydro goes down. Okay. Now, fossil fuel, we have one coal plant in Centralia. We have a few in Oregon and Montana and Idaho. And we have some gas plants. So this is the fossil fuel, also biomass. There's a biomass plant in Montana. And as you can see, they're just producing. They go up and down a little bit, but they're just producing. So they're pretty steady. You can depend on that. It doesn't matter what the weather is or anything else. Same with nuclear. Here's our one nuclear plant, the Columbia Generating Station here, Energy Northwest in Richland, right near me. And it just produces 1,200 megawatts continuously. Okay, it never stops until it refuels every couple of years. And then here's wind. So here wind comes up and down. You can't plan on it or any. It just depends on when the wind is blowing. And you notice when wind comes up big, hydro goes down big. All right. So the system operators are simply using hydro to adjust for the wind that comes on. You can't plan for the wind coming on. So they say, okay, wind comes on. Okay, we'll shut down hydro. They don't do anything else. They don't shut down gas. They don't shut down coal because it's harder to do that. So they use hydro to load balance and load follow and deal with the intermittency of wind. And so wind comes up, load goes down, wind goes down, hydro goes up along with the load. So all wind is doing in the Pacific Northwest is replacing hydro. It's not replacing fossil fuel like it's supposed to. So you have to ask yourself, is it really worth putting a lot of wind into the Pacific Northwest if all you are displacing is another renewable? This is not a trivial question because it costs a lot of money to put wind in. So unless you are displacing fossil fuel, you need to seriously think about placing wind where it's not replacing fossil fuel. So resource adequacy. So the big term in energy parlance is resource adequacy. Do you have enough resources to adequately balance your grid, whatever area you're talking about? So we use this so we do resource adequacy studies, okay, and projections. And so one of the issues, like I was mentioning, is that 95% of the year, everything's fine. You can don't have any problem. You have more resource than you need. It's just, when you have these maximum electricity demands or these peaks that are associated with the coldest and the hottest days of the year. And we're seeing that because we're seeing a lot more extremes in weather across the country. You can say it's due to global warming. You can say it's due to El Niños. You can say it's due to whatever you want to say it's due to. But we are getting more extremes, and you have to plan for those because that's when things happen. So we do probabilistic analysis. We do risk management. Blah blah blah. And we decide when we're going to make major investments in a new power source or a new high voltage transmission line or whatever we're going to do. So inadequate power means we risk blackouts, destruction of infrastructure, things blow up, they still blow up, and life-threatening situations for people, like during heat waves, people die. During cold snaps, people die. Not that many, but too many. Now, the Washington State Legislature passed the Clean Energy Transformation Act. It's a great one. I love it. In 2019, it says we have to eliminate coal by 2025. So the Centralia coal plant will be closing in 2025, no question. All right. And then we need to be carbon neutral by 2030. So the gas plants either have to close or they have to install carbon capture, which we do not have yet. Okay, I mean, we have it theoretically, we've done a few demonstrations, but we do not have that as a capability for all natural gas plants yet. We should, I wish we did, but we don't. Now, a lot of the people in the industry warned that losing baseload sources like coal would cause a problem if demand increased, which is going to occur by 2030. Now, the concerns come from retirements of coal generation. I'll talk about that even more. Deepening dependence on wind and solar. So that's going to happen. No question about it. We are going to install more renewables. No question. So we're going to have, the grid operators are worried about that. There's an anti-fossil fuel sentiment in policies and public opinion. That's fine. I have an anti-fossil fuel sentiment. But the problem is we've been using natural gas a lot to solve this problem. And we've been saying, hey, natural gas is better than coal. No question. Of course it is. It's a lot better than coal, but it still produces a lot of CO2. And CETA, this legislation, is going to say, no, you can't use natural gas either unless you use carbon capture. So we're not going to do any new natural gas generation, although I'm not sure that is actually going to be the case. When things get tough, we may just back off and start building more gas plants, because you can throw a gas plant up really quick. And then, of course, the anti-nuclear sentiments are also in policies and public opinion, which is insane, but that's a whole nother issue, which we'll get to. So, and the reason I bring that up is because the new small modular reactors are as good as natural gas at load following or buffering renewables. They were designed for this, right? Now, SMRs can't melt down. And I can say that technically they cannot melt down. Okay, and all the other scary things we fixed. We haven't been idle in the last 30 years. So we know how to do this. We just have to build them. We're not building them. Okay, we're still testing and we're still regulating and all this. We're not building yet. And until we do, we're not going to solve this issue. Now, here are the coal plants that are either retired or going to be retired. And this is the date of their retirement year. So again, we closed 4 of them, I'm sorry. We closed Centralia 1 last year, Boardman as well. So I'm sorry. We've closed 5 coal plants in the last 3 years. and we are going to close about 10 more. This is a huge amount of capacity. So this is 6 gigawatts or 6,000 megawatts capacity that we're going to be losing before 2030. That's why everyone's worried, because this is an awful lot of capacity, and we don't have the extra capacity to deal with that. And when I was talking about capacity factor, so to replace 6,000 megawatts of coal means you're going to have to install 30,000 megawatts of wind, and you're still going to have to back it up during the intermittency. So this is not trivial. Today, Washington State exports electricity because of our hydro, but we anticipate we will become a net importer well before 2050, probably about 2035. And over 40% of our electricity will come from states like Montana and Wyoming. We're actually assuming they're going to still have coal plants. Okay, we really are assuming that, and gas plants. The grid operators are assuming that we're going to fail to decarbonize, because if we do decarbonize, we're going to be in trouble with the grid. So this is a real, damned if you do, damned if you don't kind of thing, because we are not decarbonizing correctly. Now, all of the decarbonization scenarios expect wind to eventually dominate more than 50% of the energy sources in the Western United States. That is incredible. I find that incredible. What's gonna load follow them? I mean, there are times during the year, there are times during the week that the wind is not blowing anywhere in the Western United States. So if we're over 50% of our capacity is in wind, where are we going to get the extra energy from? We're going to import it from the East Coast, Canada, Mexico. I mean, where are we going to get this when the wind stops blowing? This is rather insane. And one of the big issues is that the public still hates transmission lines. So when you say, and you have to have many more transmission lines with renewables, because they're usually sited far away from where the electricity is used. So they're usually sited far away from Seattle, or far away from Sacramento, or far away from the users of the energy. And so you have to install high voltage transmission lines to get the electricity to where it's used. And we keep voting that down as a public. Okay, so this really kind of shows you not holistic thinking. Okay, I was in New Mexico. I lived in New Mexico for 10 years at Los Alamos and down at WIP. And we built a huge 100 megawatt solar array in the middle of the desert. Wonderful, excellent. And then the public kept voting down the transmission lines to get that electricity to Albuquerque. Okay, so it was actually completely useless. I mean, that is not a trivial thing. You cannot pick and choose what you like and don't like. You got to really understand the whole system. And if you're going to install a lot of renewables, like we will, then you better install more transmission lines, or we're going to have problems. Now, the Northwest Power Pool considers an outage risk of less than 5% to be safe. So if the risk of blackouts is less than 5%, that's pretty good. That's what we consider safe and don't have to worry about it and all that kind of thing. But they warn that when we close Centralia and a few of the other coal plants by 2025, our risk is going to go up to 26%. That is outrageous. That is an outrageous risk of blackouts across the Pacific Northwest. And this right there scares the heck out of me. Right there. That's it. If you know nothing about this talk tonight, we're going to go from less than 5% to 26% risk of power outages in 4 years. And we have no installed capacity coming online before 2025. So we're going to have to pay through the nose to import electricity during these time periods. And of course, most of the surrounding states are going to be in the same problem because we all have kind of the same weather. The increased load to generation ratio will come from the loss of coal plants, a slow increase in population. Our population has been steady for a long time, and it is increasing now. And then an expected large increase in electric vehicle use. I love electric vehicles. It's the only way to get rid of petroleum use is to go to electric vehicles. I mean, hydrogen, blah, 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 whatever. Other thing, biogas, it's electricity. Okay, that's what we have to replace internal combustion engines. We don't really have enough lithium, as I was mentioning, or graphite or cobalt, but that's something we can do. But if we're going to increase electric vehicle use, we're going to need more power. And that's going to pretty much, in Washington State, amount to about 10 billion extra kilowatt hours a year. So here we are facing a shortfall and higher risk of blackouts, and we need another 10 billion kilowatt hours a year to charge our electric vehicles by 2035, because everyone says we're going to be off internal combustion engines by 2035, if you can believe that. California actually legislated that. I'm sure they would legislate against tornadoes if they could, but it doesn't matter. I mean, legislation works wonders on things that you can actually control, but not on things you can't. So we are going to have to come up in Washington State and the Pacific Northwest with another 10 billion kilowatt hours a year to charge electric vehicle use that we expect. And that's the equivalent of what comes out of our nuclear power plant here in Richland, or full SMR set, or 2 gas plants. So this is not a trivial amount of power to charge our electric vehicles. Okay, so the problem with wind. On an annual basis, wind power plants generally generate energy equivalent to about 25 or 30% of what they would if the wind blew constantly. Come on, stop it. I'm sorry. I'm hitting the wrong buttons here. So I mentioned that the capacity factor of wind in Washington State is about 27%. Okay. By comparison, the nuclear plant here produces 95% of its maximum nameplate rating per year. So, according to the most recent E3 Northwest Resource Adequacy Study, the effective capacity of our 7,000 megawatts of wind power in the Pacific Northwest is only about 7%. It's not 27 or 30%, it's 7%. So when things are really bad, the coldest and warmest days of the region, you can only depend on 500 megawatts of wind showing up out of 7,000 megawatts. Now that's a little frightening, actually. That's what happened in Texas. Now, you probably heard all sorts of discussions of why Texas had the rolling blackouts during the cold snap, that it wasn't because of the wind, that it wasn't because blah. No, it actually was because they have so much wind. They knew it wouldn't be working, but that doesn't mean it's a good thing. I mean, they knew they would only get about 7%, 10% of their wind during the cold snap. So they were depending on natural gas. The problem is they don't have enough natural gas pipelines. And they didn't have enough supply, so that when it got really cold and everyone was turning their thermostats up and they were burning a lot more natural gas to heat the homes, then the amount of natural gas available to power, to load follow the wind, was not there. Okay, so it's not like you can't say, oh, well, the wind, we knew the wind wouldn't be producing power, so it's not the wind's fault. No, it's a holistic issue here. Okay, if you have too much wind and not enough buffering and not enough gas pipelines and not enough gas plants, then you have failed to provide adequate resources to that region when you knew you were going to have a cold snap. They had a cold snap 10 years ago. They did the same thing and they didn't learn. So again, nature does not like stupidity. Generally, if you're in the forest and you're stupid, you die. Society is a little different, okay? The individual is buffered from the vagaries of nature by the overall society, but if society itself ends up being stupid, then, things can go bad. So it matters where you put power plants. And that's because it matters how you build them. Now, the amount of steel, this is metric tons per megawatt installed. This is concrete, cubic meter, which is about 2 metric tons per megawatt. This tells you the different energy sources, the 6 main ones. Hydro requires a lot of concrete, but not much steel. Solar requires a huge amount of steel, but not much concrete. Wind requires both. It requires a lot of steel and a lot of concrete. Now, coal, nuclear, and gas doesn't produce much. Gas just doesn't take much. It doesn't take much steel, doesn't take much concrete, doesn't take much anything else. You could throw a gas plant up in a year because it doesn't take many materials. And that's why everyone loves gas, because you can just throw up a gas plant, in a year, and it's cheap because of that. So when you're talking about installing or replacing, say, coal with wind, you need to make sure you have enough steel. We don't have enough steel. That's one of the problems, along with the other materials, copper and lithium and neodymium and everything else. So if you're going to get the biggest bang for your buck of steel, then you need to put wind where it produces the most energy, where the capacity factors are 45% or higher. So you need to put them in Tornado Alley, right? This is Tornado Alley. It's called Tornado Alley for a very good reason. It has a lot of wind and it's always blowing. All right, so that's why wind turbines get twice as much energy here as they do in Washington State. So if we don't have enough steel to build all the wind we need to, then you need to put it where you get more energy per ton of steel. Then you have to build high voltage transmission lines to get that to where the energy is needed. And that's okay. We can do that. We know how to do that. We just have to do it. Now, the same thing with solar. Say, you don't want to build solar in the areas that are green. Okay, that is dumb. Okay, it's dumb. Okay, solar produces twice or 3 times as much energy here. Now, I have solar panels on my roof. I love them. They're great, but they only have a capacity factor of 10%. That's not very good. Whereas the capacity factor for Ivanpah or Buffett's huge PV solar array are 35%. Okay, I only get 10%. So I shouldn't have solar panels on my roof. It's kind of dumb, but I wanted them. Judith thought it'd be great. We need some street cred on renewables. Okay, that's great. Love it. But if you're going to produce a lot of solar, you better put it where it's red or orange. That's just come on, this is common sense. This is not rocket science. And the same thing with dams. Now, it turns out these are all the dams in America that are not powered. Okay, there's a lot of capacity here. It's more than all the hydro we have today, all the hydro power we have today. If we just powered these, right? You don't have to build any new dam. The dams are already there. You simply have to turn them into hydroelectric dams. So we could double the amount of hydroelectric power in America, which is great for load following renewables, especially in this region, by not building a single new dam. We just have to power what we have. Already have the environmental impact statements. The public already knows them. These dams have been there for decades, so we know they're there. So again, just a little common sense in planning would go a long way, because hydro is one of those great power sources that we need, especially in light of all the renewables, the other renewables, wind and solar, that we're going to in place. Now, as far as high voltage transmission lines, probably unknown to you, direct current lines are actually better than AC lines, alternating current. So direct, contrary to Edison and Westinghouse, 130 years ago, DC lines are actually better. They lose less power during transmission over long distances, and they actually cost less the longer the distance. Okay, so we have not been building high voltage transmission lines in America because no one likes them. The only one that we've ever built in the last 20 years was a high voltage direct current line from Texas to Tennessee. And it's great, but we need to do more of these. If we're going to install more renewables in places where they actually produce electricity, you need to put in more high voltage transmission lines, and they need to be DC. Okay. Let's see. So, Washington State and the Pacific Northwest in general is pretty good in terms of CO2 emissions. I mean, Washington State is better than everyone else. Used to be Vermont we'd go back and forth between Vermont and Washington State, but Vermont closed their nuclear plants, so now their CO2 emissions shot up like crazy. So we're already pretty good. I mean, you know, people say, "Oh, we have to do this." It's like we're pretty good, actually. Very, very good. And that's because most of our electricity consumption is non-carbon emitting. Most of, hydro, nuclear, some wind, one coal plant, and 2 gas plants. That's really not bad at all. In fact, most of our CO2 emissions come from the transportation sector, as you'd expect, because we still burn gasoline. And so the only way to really drop our emissions statewide quickly is to replace internal combustion engines with electric vehicles. Because our electricity is so low carbon, that means that your electric vehicle is going to be low carbon. Okay? That's not the case in areas that produce their electricity from coal. If you get an electric vehicle in Kentucky, say, you might as well not bother, because all the electricity is coal generated. So you're not doing any good. And truly, it's actually, you're not doing any good. But in Washington State, you are. So if we look at, let me get to the geopolitics issue here. So this is what humans look like on Earth, generating 24 trillion kilowatt hours a year. So we are presently at 24 trillion. We're going to go to 35 trillion plus by 2040. Maybe even much more than 40 trillion by 2050. So we're going to be generating a lot of electricity, a lot more electricity. So when we talk about decarbonizing, we're not just talking about decarbonizing our present 24 trillion kilowatt hours. We're talking about decarbonizing what we will be at, which is 35 trillion or more. So this is even more difficult than people think now. But it depends, so it depends on where you live. Again, here's the world distribution by type. We're 2/3 fossil fuel, 1/3 split between hydro and nuclear, but we're 2/3 fossil fuel. Now, transportation is all petroleum. So that's why I say you want to get rid of petroleum, you just have to go to electric vehicles. And you could do to some biogas, you could do some hydrogen, but it's essentially electric vehicles that will save us on the transportation side. But we'll stick mainly with power production. It depends on where you live. The United States is also 2/3 fossil fuel, but a little bit more nuclear, a little less hydro. Wind's coming up. But it depends where you live. So Washington State is mainly hydro. Again, only 1 coal plant, 2 gas plants, 1 nuclear plant, and a bunch of wind. West Virginia is the most carbon intensive, and Illinois is the most nuclear. The European Union is a little bit more nuclear because of France, less hydro. Korea is significant nuclear, and before Fukushima, they were going to go to 60% nuclear, which they should do, and they probably will do. They wanted to be 60% nuclear and get rid of coal. And the reason they wanted that is because Korea, like Japan, has no resources to speak of. They have no fossil fuel resources. They have not very much hydro resources, hydroelectric. They don't have much biomass resources. They don't have anything. So if you don't want to be completely dependent on China or other countries for your energy supply, you need to be nuclear. And that's why they plan to be 60% nuclear. Now, China, 4% nuclear doesn't look like much, but they're breaking ground in a new nuclear plant every month. They are building nuclear like crazy. So by 2040, they anticipate 200 nuclear plants, which would bring them up to 30 to 40% of their energy from nuclear, which would be amazing. They want to get rid of coal, but they can't because they have too many people and they have too much demand for power, and it's still rising because they still have a lot of poor people that need more energy, and they're going to give it to them. That's it. They have a lot of hydro, and they're building more hydro. So they're building more hydro and nuclear. They're building more renewables than everyone else in the world. I mean, they are dwarfing everyone in the world with solar and wind, no question. But it's still not enough. So why do we care about any of this? Well, we care about global warming. We care about climate change. This is a very busy slide. I apologize for it. It's climate change over the last 500 million years. And in order to fit it all on one graph, you have to change the scale here. So this is thousands of years, hundreds of thousands, millions, tens of millions, hundreds of millions. Now, what should pop out, and this is the 1850 global temperature standard, so the baseline. What should jump out at you is that for the most of Earth's history, it has been a lot warmer. I mean, it's been hugely warmer. Okay, we are in a bizarre, rare, cold period for the last 10 million years, and we've had glaciation for the last 2 million years, which is a rare event on Earth. Glaciers are very rare on Earth. And so we're coming out of it now fast. Again, this is an expanded scale here. So if you put the scale back like it is in the past, then that would be a vertical line in the last 100 years. So we're coming out of it fast. And that's because the absolute temperature doesn't matter. Okay, it doesn't matter at all. The absolute amount of CO2 in the atmosphere doesn't matter. It's the change. It's the rate of change that matters. I don't like change. My cats don't like change. Biota does not like change. If you change too fast, generally you die. If things change too fast, you die. It's called extinction. It's no big deal. Happens all the time, unless you're being extincted. But that's what counts. It's not the amount of CO2. It's not the absolute temperature. If things change slowly, the biosphere on Earth has the chance to adapt. And that's all well and good. But if it changes too fast, like it's been changing the last 100 years, then things get pretty hairy. And that's what's going on. So it has nothing to do with the absolute temperature or the absolute amount of CO2. It's the rate of change. Now, when talking about climate change, I hate modeling, hate to bring in models, but these are the two models everyone talks about, A2 and B1. So A2, the red line, means we business as usual, nothing changes, okay? We are 87% fossil fuel primary energy. So if you include transportation with electricity and heating, we are 87% fossil fuel in the world now, 87%. Okay, we haven't made much of a dent. Now, if we're still at 87% for the next 50 years, this is what's going to happen. And it doesn't look very nice. Now, B1 is we do everything we say we're going to do. It's still not that great. Okay, I hate to say that, but this is not that great. It still gets warm. But this is where we talk about keeping it down to a 2 degrees centigrade or 3.6 degree, 4 degree Fahrenheit increase in temperature by the end of the century. We talk about decarbonization, and that gets us the blue line. That's if we do everything we think we're going to do, everything we want to do. So the amount we deviate from that is simply the difference between these two lines. So it's still, if you say, oh my God, this is terrible, you might as well do nothing. No, that's not good. No, we want to do something. So everything we do, the more we do, the lower we go from this line down to this line. And that's good because this line is pretty bad. In fact, if you look at the effect in the United States, this is what happens. So this is B1. This is we decarbonize the way we say we're going to, or we don't. That's the difference here. And there's a significant difference. Okay, this is bad enough, but this is horrible. Okay, if you want some really bad things to happen here, this is it. Now, Washington State, because of our marine climate, is a bit ameliorated. So we do pretty good here. Even in the bad times, we're pretty good. But yeah, Eastern Washington, where I am, is pretty rough. Now, this is the last global warming slide. This is the decarbonization path we need to take in order to keep to B1, that keep it to just 2 degrees Celsius rise in temperature, or 3 to 4 degrees Fahrenheit. So we had to start decarbonizing in 2011, and we had to decrease the amount of CO2 emissions almost 4% a year until 2050, when we could still have a fair amount of anthropogenic emissions. Well, we blew that one. So 2015 came along. Now we have to decrease 5% a year. And then we have to go to zero before 2050. Well, we blew that one too. So here, 2020 came around last year, and we needed to start decreasing 9% a year and go to zero by 2040. That's why everyone talks about 2040. You keep hearing that date, because that's when we have to decarbonize to zero. And we have to come down 9% a year. Now, trick question here. How much are we decarbonizing? How fast are CO2 emissions coming down? I wish I could do a show of hands. Trick question. We are not decarbonizing. Every single legitimate projection, and I'm not talking about, see, these are not projections, these are wishes. This is what we'd like to happen. This is what has to happen in order to decarbonize and keep temperature rise about 2 degrees Celsius. But the projection of what's actually going to happen, I haven't seen one that does not have CO2 emissions increasing until 2040. In fact, only after 2040 do any of the scenarios look to decrease emissions. And that's way too late. So we are not moving in the right direction. So all we have to do is get rid of these and bring these up. It's actually quite simple, but not easy. We have to decrease these. In fact, we have to get rid of them. And we have to bring these up. And at that point, you have to stop this Pollyanna crap about you can pick and choose which ones you want. You can't. You need them all. If you can't throw any one of these out. You can't say, well, I don't like wind, or I don't like nuclear, or I don't like geothermal. You can't do that. We need them because these are so prevalent and their emissions are so large that you cannot do it with 1 or 2 or 3 of these. You need them all, period. And we're not doing that. That's one of the problems. We keep fighting amongst ourselves about which one of these we like better. I'm sorry, we don't have that luxury. So, that in mind, I've set you up. What are the fastest growing energy sources in the world? Anyone want to get into the chat room? And I can't see the chat room, sorry. What do you think are the fastest growing energy sources in the world?
Just for now, you can unmute yourselves. Go.
Come on, it's not a trick question. Just, what do you think is the fastest growing energy sources in the world?
I've seen this before, so I won't cheat.
Good. Come on, shout it out, people.
Wind.
I say gas.
Coal.
Coal.
Oh,
yeah.
I'm wounded. Yes, it's coal. It's coal. It's still the fastest growing energy source in the world. Followed by, oil. Sorry, oil is the worst. Then coal, then natural gas. And down here, yeah, these are coming up. I mean, renewables are screaming up here, but it's still small. I mean, it's way small. So maybe, if you extrapolate this line, but you'd have to extrapolate these lines too, because these are not turning over anytime soon. And that's because of the third world. I'm sorry, that's old terminology. Sorry, the developing world. The developing world is still building coal, not because it's cheap. Coal is simply the only thing you can install in a country that has no infrastructure to speak of. You don't have gas pipelines, you don't have high voltage transmission lines, you don't have all the other stuff that you need for everything else except coal. You need coal, you need coal-fired power plants, you need rail lines. That's it. And then you got it. So if you're a poor country with no infrastructure to speak of, coal is all you can do. Unless the developing world comes to your aid and says, no, we'll pay for it. But we haven't been doing that. So they've still been in placing coal. Of course, oil, it's all for internal combustion engines. Now, if we talk about using wind to replace coal and oil, so not natural gas, but we'll just do coal and oil, it's going to require 20 million megawatt turbines. 20 million, or about 10 billion tons of steel. Now, what is the global output of steel per year? A little over 1 billion. So we're going to take 10 billion tons of steel just for wind turbines, but we only produce 1 billion tons of steel a year. Okay, how likely is that? So no more cars, no more buildings, no more golf clubs, well, they're titanium, no more anything that uses steel. We need all that steel for wind turbines. That is unlikely in the extreme. You could say, okay, well, we'll quadruple the number of hard rock mines that produce iron ore. Well, that's not very nice either. People are not going to go for that. So we're kind of in a bind because there's other things associated with these energy sources besides their name, besides their CO2 output. So if you're going to build a lot of wind turbines, you're going to need a lot more steel than we have, and we are not doing that. We are not preparing for it. You need to prepare for this stuff, and we're not. In fact, iron mining has gone down, which is weird. Okay, so how do we achieve a low carbon future in Washington State? Mike, let me just kind of stop here. We already have. I mean, again, like I said, we are the lowest carbon emitting state in the union. So one thing that we've been doing nicely is agriculture and industry have decarbonized significantly in the last 30 years. We've done a very good job of that, as well as, of course, most of our power is low carbon. So we've been doing pretty well. We're going to close our only coal plant 2025, so that's going to eliminate half of the emissions from the power sector. So gasoline, as I mentioned, is our biggest, gasoline and diesel is our biggest carbon source, and electric vehicles are the best way to do that. Now, I have talked for an hour. Do you want to stop here? Go to questions?
I have collected quite a few questions.
Good.
So let me give you a quick break. And Chelsea Catan asks, what about increasing public transit use instead of electric vehicles? And of course, this is definitely possible. It would have a huge impact. Unfortunately, our current build out of transit in Seattle, the biggest in Washington State, is going to be delayed by 5 to 10 years due to an $8 billion budget hole. Yeah. ST4, and I'm going to take over sharing for just a moment. Oops.
Yeah. You want me to stop sharing?
I got it.
Oops. Okay, good.
So ST4 is every path on this map which is not black or light gray. So ST4 would be a couple of different lines. It would be 1 to 3 of those lines. And this is what Seattle Subway calls our ST3 complete, our ST complete map. And so Seattle Subway is a wonderful volunteer opportunity, as well as Seattle Friends of Fission, but Seattle Subway focuses on transit advocacy. So this is that plan to replace an enormous amount of ground vehicles with mass transit, and we're just not putting enough money into it. Construction costs and revenues are costs are up and revenues are down because of the current situation we're in. So,
yeah. No, mass transit is fantastic. I mean, you need it. I mean, there's no question about it. And a lot of big cities like Shanghai and others around the world have very good mass transit systems, and they're electric, which is great. And so, yeah, so we need to do that. No question about it. We're just not doing it.
And let's see. So other questions I've started to gather. We've got, here's one for you. Greg Smith asks, what about geothermal?
Yes, geothermal, of course, it depends on where you are. Geothermal and hydro are both very dependent geographically and physiographically on where you are and how close you are to a heat source in the subsurface. So traditional geothermal, there's some very nice plants in California. Philippines are 50% geothermal, which is actually quite nice, but they're in a bunch of hot spots and on a downgoing slab, so that's pretty good for them. We don't have a lot of potential geothermal in the U.S. unless you go to what's called passive geothermal. And I'm going to do a Forbes thing on this soon. If you have enough land, okay, so say you're in a suburb and you have a big yard, or you have a park and everyone agrees to this, you could put water pipes down about 4 feet and run them up and down, up and down, up and down, so that water passing through those pipes reaches the geothermal temperature 4 feet below the surface, which in Washington State is about 57 degrees. So you have your water starts at 57 degrees. So if it's really cold out, you're not increasing the temperature of water from sub-zero or near zero up to what you want it. You're starting at 57 degrees, which is pretty good. So it takes less energy. Also, if it's hot out, you have a source of water that can cool your home passively that's at 57 degrees. So this is called passive geothermal. It's really great. And we need to do more of that. We don't have a lot of geothermal, though, in terms of power plant or size. Okay, that type of geothermal. But again, we can do an awful lot with the passive geothermal.
Yeah, a comment from me. There is a study from Chris Clack, of course, wonderful stuff, and he can only get 10% of our energy demand using just enormous advanced geothermal reserves. So this is a lot of drilling, a whole bunch in the southeast, in fact, and it's only 10% of our demand. So next question. Go ahead.
Right, and one of the problems with geothermal is that you salt up really quickly. It's really the subsurface doesn't like you taking away its heat. Okay, it does some very strange geologic things, and so those geothermal wells tend to salt up. There's a question here that I can see. Wheels to wheels efficiency of electric vehicles is so superior to internal combustion that it's not true there's no advantage. That is absolutely wrong. I'm sorry. Yes, the wheels to wheels efficiency when you're talking simply about operation, but now when you're talking about building batteries, building electric vehicles, there was a very nice study done recently. Can't recall who did it, but it showed that electric vehicles aren't much better than internal combustion unless you are 100% charging them with zero carbon. Okay, so yeah, they're efficient, much more efficient, but it actually takes a lot of carbon to make a battery. A lot of carbon. So you need to factor that in. So it's not just the manufacture of the car, manufacture the batteries, and then the operations.
When I did the math on that myself, I with my layman's terminology, I came up with about 60,000 miles to break even, at least. MJ asks, what about ocean energy? And I know that I recorded a wonderful little session with our friends from Cascadia Climate Action with a startup in Bellevue, Washington. And late night after that presentation, we sort of commiserated, and I asked, well, what's the total scale? And he said he would be fantastically pleased if ocean wave energy got between 2 and 5% of the global energy demand.
Yeah. And again, it's great. I love it. It won't be here in time. I hate to say that most of the things we need will not be here in time. If you don't do this by 2040, I won't say it's not worth doing anything, but you will severely restrict the advantages we could have if you wait 30 or 40 years to do this. And tidal energy, wave energy, all this new stuff is great, but it's not out there yet, and it won't be out there for 30 years. Same thing with fusion. Fusion is great, but it won't be here in time to solve this particular problem. Now, if you think, Star Trek, whatever, talking about 100, 200 years from now, things will be quite different. But that won't help us in the near term.
But
things will be quite different.
Even new nuclear is difficult. It's difficult to propose, but we can scale it up, like France has shown. Right. But the best thing we have right now is to prevent existing nuclear from shutting down. So let me give a quick shift to that. Is we're looking at Diablo Canyon, and before that, in fact, a very immediate problem. So if you have friends and family in Illinois, please contact them and tell them to tell their legislature, please preserve Byron and Dresden nuclear power plants. Illinois is headed for a really big catastrophe unless we solve that. The next question from Arvia.
Yes, and
go ahead.
I just need to say that shutting down Indian Point in New York was totally insane. I mean, there was no risk to New York City from Indian Point, and it produced half of the city's energy. Half of New York City was powered by Indian Point nuclear power plants, and they're gone. I mean, this is insane. And I don't know, they expect to import hydro from Quebec. Really? Quebec's going to have problems of their own here. And the rest of New England is trying to import hydro from Quebec because they keep doing stupid things like shutting down nuclear and not building gas pipelines. So New York's going to be in trouble because of this, and there's no way around it.
Yeah, Pickering units 1, 4, 5, and 8 are set to be shut down by 2025. So yeah, Ontario is going to keep all of that hydro for themselves. The next question is, Arvia, could you ask about potential for energy efficiency and for buildings in existing and new conditions? And I think there was another efficiency question. Let me get to that. How much
efficiency is the easiest, cheapest way to do it, to gain here. It's great. And we have been pretty good. I mean, talk about the efficiency standards in home appliances like refrigerators and washing machines and stuff. It's really, we have done fantastic there. And we will continue to do that. But that only gets you to some point. Then you have to say, okay, that cuts our load. But with the load we still have, what are you going to do? How are you going to supply that? So yes, efficiency is the easiest, cheapest thing to do, and we can probably gain 10% of our total emissions from efficiency gains. But you still have to replace fossil fuels.
William asks, how much will vehicle to grid help our storage situation, basically?
Vehicle to grid, good question. Shanghai is an amazing city, and it has a smart grid, and it has an awful lot of electric vehicles. So all you do in Shanghai is you plug in at home the time of day you want your vehicle to be fully charged. All right? You say, I need it fully charged by 8 a.m. because that's when I'm going to go to work. Okay, and everyone does all this, and then the grid uses all those electric vehicles as a storage battery, draining and charging and draining and charging as needed, as long as you get your vehicle charged at the time you want it charged. It is brilliant, absolutely brilliant. That's why we need a smart grid, but we need a smart grid. Okay, we don't have a smart grid. So again, most of the things we can do, we're not doing. And a lot of the things we should be doing, we could do, but we're not doing. And a smart grid is one of those things. And it'll only cost, what, $1 trillion? I'm not being funny. Actually, most of the things that we talk about take about $1 trillion. And that's, it's not a trivial amount of money, but it's doable, especially since our GDP is 15 trillion and the total, no, I'm sorry. Our budget is 15 trillion. Our total GDP is like 45 trillion. So we should be able to do this. It's going to cost. People are not going to like it. But we need to do it. We need to spend the money to do it. And a smart grid is one of those things.
Great. So we got some questions from our friend Christopher Bergen, who's watching on Facebook. Can most of pumped hydro water be reused, or does it evaporate? And what's the evaporative loss?
It's not that big. It's kind of like a river. So the evaporative loss from rivers or from ditches, like I have out here behind my house, are not very high. So we learned that a long time ago. The efficiency loss is simply pumping it up, and using, you don't get back 100% of the energy you've made into potential energy by raising, a mole of water to 100 feet. So the efficiency losses are much more important than evaporative losses. So yeah, I wouldn't worry about that. That's not a big deal at all. We actually proposed to put a pumped hydro storage here near me on the Columbia River, and of course it was voted down. Okay. So what are you going to do?
So RV has got some great questions. How much of a dent in these infrastructure issues, or in these issues in total, are addressed by the infrastructure package?
Good point. Some of them are, and some aren't, of course. There's about $38 billion, I think, set aside for new nuclear, which is great. There's some set aside for new transmission. I apologize for not knowing the details or being able to recall the details of the bill, but it's pretty good. It's not bad. It's nowhere near enough, but it's not bad for a beginning. Or I should say we need twice as much. Put it that way. We need twice as much now.
There's a question from MJ. What are your recommendations for us to ensure electric capacity and sufficiency, and also sufficiently reduce climate warming scenarios? What sort of individual steps can we take?
Well, that's it. That's the big question. Okay. Don't shut down non-emitting sources. Okay. You got to stop that. Don't build new coal. We are not doing that here, but they're doing it around the world. Okay. Go to efficiency, go to electric vehicles. I mean, everything we've been talking about is good, but how do you do it at the magnitude you need it done in the time frame you need it done? And that's the big thing. That's the difficult part. Everyone's not on board with everything, as you might expect, especially in a divided country like this. I mean, we can't do anything, it seems, in a national way anymore. So it's up to the individual states. And Washington State is quite aggressive in its decarbonization goals. That's great. I love it. I want it. But just like the power pool says, we're in for some trouble there if we don't plan better between 2025 and 2030. We're going to have rolling blackouts if we do not come up with a better strategy for emplacing new generation. And that new generation should be small modular reactors, but probably won't be, not by 2030. We could put one small modular reactor out here right on the same property as our existing nuclear, which would be great because all the EIS is done. People around here love it. Nuclear power is great. It's the safest form of energy there is. You wouldn't know that from Twitter, but it is. And so, we should do that. We should not. I'm kind of conflicted in terms of gas. Shut down coal. Coal's dirty in many, many ways beyond carbon. But natural gas, if we shut down our natural gas plants, there's nothing to replace them. But we're going to be in trouble. And so I'm worried about that. I'm worried about closing 2 gas plants. The plan was to replace Centralia with 2 new gas plants, but the CETA legislation has kind of kiboshed that. So I don't know what we're going to replace it with. It can't be wind. I mean, we couldn't build enough wind turbines to replace them, and wind turbines here just don't do anything. So yeah, I'm worried. I'm quite worried.
There's a couple questions came in. Bob says the infrastructure bill has a large amount of funding for hydrogen. How much? And so I want to know how much of that hydrogen is coming from electricity and how much from gas.
Good question. It's coming from gas. I mean, we produce hydrogen from methane. That's it. We don't produce it from water because it takes so much energy. Producing hydrogen from water using electrolysis is about 17% efficient, which means you lose 83% of the energy you put into creating the hydrogen. So that is really not very good. I mean, if you use only wind turbines or only solar panels to produce it, I guess that's okay, except that the cost of solar and wind is not that cheap, especially if you waste 83% of it. So that's a problem. So now, if you use biogas to produce hydrogen, that's better. We don't have enough biogas to significantly make a dent in our petroleum use. So again, this is kind of the same issue we have with everything else. Great on paper, great in theory. We haven't put it into practice at the level it needs to be put into practice. If we did, that would be great.
So let's do one more question from the chat, and then I'm going to shut down our broadcast and we can, turn on our microphones and cameras and say hi to one another. This one will be, John asks, are there large solar projects in New Mexico or elsewhere in the Southwest that are lying fallow because of no transmission?
Oh wait, I'm sorry. Could you repeat that?
Are there any solar projects? I guess I'll ask in general. Do you know of solar projects that are lying fallow because of a lack of transmission?
No, they're just not planned. So again, if you're doing this, if you're Warren Buffett and you spend $2 billion putting in a huge solar array like you did, then you're going to wait until you have the transmission lines. It's all set up. You aren't going to do it without it. So yeah, so there's none waiting for it. Except the example I said in New Mexico when I was down there. It's 15 years ago now. So they lost their shirts on that. So they probably people are much more cautious. So investors are very cautious. This is, in fact, if you want to look at the trends of what's actually happening, you look at investors because, investors are not stupid. They don't waste billions of dollars on something that isn't a good bet. And venture capitalists, if they don't get a 20% return in 5 years, they won't invest. So, just look at the money that's going different places. And that'll tell you what's actually happening and what's likely to happen.
Great. So just for everyone on twitch.tv, I'm going to send us off to the Humanist Report. Everyone on every other network, this will be the end of our broadcast. So thanks so much for checking in and listening to Dr. James Conca from Forbes and address us on the subject of energy.
Great talk, Sam.
Thanks so much. Good audience. Good crowd.
Yeah, Carl, why don't you say something real quick about Stand Up for Nuclear, September 18th?
That's right. We have an event coming up in Seattle, Washington, in September 18th. It will be at the Westlake Park South portion, the portion near 4th and Pike, and we would love to have all of your support because we are going to stand up for nuclear. We want to see more nuclear energy. We want to electrify everything. and especially transit, because that's our biggest source of emissions. So please stand up for nuclear with us September 18th in Westlake Park. And of course, you can also, if you're not from Seattle, you can look around the country. There are tons of cities doing Stand Up for Nuclear in September at standupfornuclear.com. So thanks everyone again on the broadcast. We're going to send you off.
Thanks.
Thanks, Jim.